Okay, so let's give you a quick review for previous class. In lecture 5, actually we want to tell you how to estimate the diffusivity in materials with different types of crystal imperfection size. For example, like polycrystalline materials, what we have. So how can we estimate the diffusivity of this of the polycrystalline materials? And the term we also show you, which is entitled characteristic diffusivity in crystal imperfection size. Crystal characteristic diffusivity means the diffusivity along specific diffusion path, so can be diffusion through the grain through the dissociated dislocation on dissociated dislocation, grain boundary, and free surface. Okay, so based on these figures, we know that based on the when you take a look on the specific temperature here, we find that the diffusivity through the grain is slowest compared to other different types of diffusion paths, and the highest one would be the free surface or the grain boundary or dislocation, undissociated dislocation. And the other thing is, I grabbed some figures, want to experimental results, want to demonstrate, want to show you the material structures did affect the diffusivity of specific atoms. So the case here, the data here I show you will be the linear LiNb oxide. And what we have here is we have a single crystalline LiNbO3 and amorphous one. And also the other thing is we replace the Nb with a Ta and also have a single and amorphous one. And the vertical one is the diffusivity of the linear atoms, and the horizontal also will be the 10 to 3 divided by temperature. So also is a reciprocal for temperature. So based on this data, you can find that no matter which materials for the single crystalline one, the diffusivity of the linear is slower than that in the amorphous one at specific temperature. Okay, and also based on the slope, I believe you can fit the activation energy, right? Because this slope for sure will be correlated with the slope will be equal to negative activation enthalpy divided by K, right? Okay, so the other thing is, as we mentioned, if the materials you deal with is polycrystalline materials, and probably during your interesting temperature regime, not only one diffusion path dominate. So under that situations, probably will be the two or more diffusion paths dominate or contribute on the diffusivity of your interesting atom, right? So in that case, the log D versus 1 over T, what's the figure will be look like? So I grab the other figures here. Log D versus 1 over T times 1 to 3 or 10 to 3. And you can see we have a single crystallized silver and also have a polycrystallized silver. And the result is interesting because for single crystallized silver, the diffusivity of a silver is only, after fitting, will be only can be fitted into one straight line, right? But for the polycrystallized silver, you can fit it at least fitted with two straight lines with two different slopes. And before, the temperature is higher than this temperature. In higher temperature regime, the diffusivity of polycrystalline silver is identical with that in the single crystalline silver, which implies that during this temperature region, at high temperature region, the grain diffusion dominates. But when decreasing the temperature, we observe that the other straight line with different slope be founded. This implies that probably grain boundary diffusion contributes some on the diffusion of silver. But don't forget, for example, like at this data point, because in polycrystallized silver, we have the diffusivity at this specific temperature. This data are contributed by the grain boundary somewhere and the grain. So this data actually is a summation of diffusivity contributed from grain boundary and grain. But here we don't know the grain, but we know the contribution from the single crystalline, and we also know the final resulted diffusivity. So you can estimate the diffusivity of the grain inside the grain boundary, right? And for all the data points shown here will be the co-contribution from the grain boundary and grain. Okay, this is just for your reference. So in our textbook, actually, they put more focus on the grain boundary. So we want to introduce, there are two different grain boundary structures. The first one we call is a tilt boundaries. What this means, we have a grain 1 on your left-handed side and grain 2 on your right-handed side, and in between we have a boundary plane. And we also have a rotation axis, which is parallel with the grain boundary. And now the other thing is we have a theta. We call it is a rotation angle. So this rotation axis and corresponding, we have a rotation angle or tilt angles, and this actually the angles will be proportional with the numbers of edge dislocation we have here. So as this figure shows, if you have more edge dislocations, the theta will increase in the meantime. So this type of grain boundary, you call it as a tilt boundary, and have a rotation about and these rotation angles in a boundary plane. And the other type of grain boundary is we call a twist boundary. And also, the difference between this one and this one will be the rotation angles. This rotation angle is perpendicular to the this boundary plane, and we also have the angles theta. So the theta can be, this rotation angle theta can be small, can be larger, and that will result. You can see the diffraction patterns. The patterns or crystal patterns will be slightly different with you increasing the theta. So twist boundary have rotation about an axis perpendicular to the boundary plane. So the difference only the rotation angle is parallel or perpendicular to the boundary plane. And in this part, actually, we are interested in to estimate the diffusion in the polycrystallized materials. As we mentioned before, when we have an atom here, probably it will diffuse. In the beginning, it will diffuse through the grain, right? Then jump into the grain boundary for certain diffusion time, then jump back to the grain. So sometimes this atom will stay in the grain, sometimes it stay in the grain boundary, and also jump back to the grain. So under this situation, in lecture 4, we only learn how to estimate the diffusivity inside the grain. And we don't have any idea how to estimate this kind of if we have two diffusion paths, including the grain and grain boundary. But here, at least you know that the diffusivity inside the grain boundary is different with that inside the grain due to the gamma. Gamma prime will be different. What's a gamma prime? Gamma prime is related to the bond strength, reduced mass, and activation energy. So based on these parameters, the grain boundary, the bond strength and reduced mass in grain boundary will be totally different with that in the grain, and also the activation energy for sure will be smaller than that in the grain, right? So that will lead to the different diffusivity. The diffusivity inside the grain boundary will be totally different with that inside the grain, and for sure will be faster, right? Especially when you take a look on the explanation term. This one, if we have a smaller activation energy, and for sure the gamma prime will be higher and diffusivity will be higher. So next, I'm going to show you how to estimate the effective diffusivity in polycrystalline materials. Effective diffusivity can be the real or measurable or total or overall diffusivity of these polycrystalline materials. So how to estimate that? So before we move to the detail, we need to make a very important assumption. We assume the diffusion distance in a diffusion time t is much larger than a grain size s, which means the dxlt is larger than s squared. But sometimes people probably will ask, dxlt larger than s squared. Actually, this description is due to the diffusion length. When we estimate the diffusion length, we usually will use the square root of dt, and we compare the square root of dt is a diffusion. X0 means the diffusivity inside the grain. So diffusion length inside the grain compare with the grain size, which one is larger. So in this case will be like this. In order to interpret that, so we take the square term here. Take the square term here. Okay. Square. So become like this. So this implies that the diffusion length inside the grain will be larger than grain size, one grain size. Okay, so it implies that this means that you cannot ignore the diffusivity inside the grain. So under this situation, we cannot ignore the dxlt, right? So now we need to know if we want to estimate the effective diffusivity. It means we need to consider the diffusion path through the grain and also the grain boundary. So how to think about this? So important part will be the fraction of time to the diffusion atom spent in the grain boundary. So we use the iota to represent the fraction of time to a diffusion atom spent in grain boundary, compare with that inside the grain. So iota defines as the time in the diffusion time. The diffusion atom spend t time in grain boundary and spend t actual time in grain. Okay, so as we mentioned, when a diffusing atom diffuse through the polycrystalline material, sometimes it will stay in the grain boundary, sometimes it stay in grain. So we want to know the fraction or the difference between it spent how much time inside the grain versus it spent how much time inside the grain. So that actually is talking about the numbers of available jump site in grain boundary versus inside the grain. Available jump site is proportional with the volume of that specific diffusion channel, right? Means the volume of grain boundary versus the volume of the grain in these materials. When we talk about the volume, so the one actually we talk about would be in three-dimensional case. So what's the volume of the grain boundary in your materials? If we consider a grain, so the grain size will be, if the diameter of the grain would be s, so the volume of the grain will be s23. So how about the grain boundary? If we assume a thickness of the grain boundary is delta, and we also consider 1 grain, right? So the volume of the grain boundary will be S plus delta divided by 2 plus delta divided by 2. So will be S plus delta divided by 2, delta divided by 2 times, so S plus delta to 3, and minus the grain part. So you will get the volume of the grain boundary. Okay, so you can expand S plus delta to 3 as like this. And due to the S is much larger than delta, so you can delete this term, so you only left this term, and you use this term to minus this term, minus this one, so you got this term. And the bottom you have is S to 3, so the result will be 3 delta divided by S. And this is the fraction versus the atom span time in grain boundary versus that span time in grain. So you can use this to get the mean square displacement in grain boundary by directly times the diffusivity inside the grain boundary times iota times T. So this is the is the moving distance or moving displacement of the diffusing atom in the grain boundary. And the same idea can be performed to get the mean square displacement inside the grain. So be the diffusivity inside the grain times the time diffusion time. Actually, time t is a diffusion time, right? So inside the diffusion time, we use the 1 to minus iota, means the portion, a total exactly times to the diffusing atom span in the grain boundary, then times the diffusivity will be the mean square displacement in grain. And we sum them together and will be equals to effective diffusivity times the T. Right? So this D, use this symbol to label this D is we call the effective diffusivity, or co-contribute from the diffusivity inside the grain and also the diffusivity inside the grain boundary. Okay, so based on this, we want to give you some examples here. In most of cases, the iota is much smaller than 1. For example, the reason is the volume fraction of the grain boundary versus the grain is very small. For example, if the grain diameter what we have is in 1 micrometer, and the delta, the thickness of the grain boundary will be around 0.5 nanometer, and the order is near like by the 3 orders, right? So the iota is quite small. Okay, and so I just copy this results here and delete the t together. So we get these equations and substitute iota by this 3 delta divided by s. And due to the iota is quite small, so this term I just deleted because 1 minus very tiny stuff, I can ignore this one. So the effective diffusivity expressed like this: dxl plus the contribution from the grain plus the contribution from the ground boundary times the 3 delta divided by S. So in most of cases, people will ask, Professor, it turns out the effective diffusivity of in the polycrystalline material will contribute from the diffusivity inside the grain plus the diffusivity of the grain boundary times this iota, right? But in what kind of conditions I can directly use the diffusivity inside the grain to represent the effective diffusivity? I can directly ignore the grain boundary part. When what? When this term will be very, very, very small compared to DXL, right? So that will be depending on the value for the difference between the grain boundary, the size between the grain boundary and the grain, and also the diffusivity difference between the grain boundary and also the grain. So if the diffusivity dB is much larger than dXL by 3 order, why here I say 3 order? Because I assume the delta here is near 1 nanometer and the S is 1 micrometer, so this will be what? This term under this situation will be 1/1000, right? So if the dB is quite small, it's compatible, it's the same order with DXL, then you times this order, you can ignore this term, right? But if the dB is larger than DXL by 3 order, for example, if this is 1 and this is 1000, then under this situation, you times this, so you got 1 plus 1. So under this situation, the contribution from the diffusivity contribute from the grain boundary part cannot be ignored because it is large enough to affect the effective diffusivity. Okay? So next, I'm curious, want to ask you, which diffusion path is the dominant path for specific materials at specific temperature? How to determine which diffusion path is a dominant diffusion path in specific temperature in the polycrystalline materials? How to know that it's a dominant diffusion path will be 1 or 2? How to determine that? How to estimate that? So I will say you can measure the effective diffusivity at different temperature and plus to the log D versus T, the figure like this, log D versus 1 over T. If it turns out a straight line like this, then during this temperature, just one diffusion path dominate. But if you turn out like this, can fit it by 2 straight lines. That means in different temperature regime will be different diffusion path dominating. Okay, dominate the effective diffusivity. Okay. Then just for your reference, one more thing. The iota, the volume fraction here we just mentioned is in 3-dimensional case, but in some experimental design, probably the one you deal with belongs to 2-dimensional. So some people probably will ask, Professor, under what kind of situation we need to consider but will be belongs to 2-dimensional? If you deposit a thin limited diffusion atom on the top of your substrate, then you heat these materials up and allow diffusing atom diffuse into the substrate. And under this situation, this will be belongs to 2-dimensional diffusion, right? Because this is just alone this stuff, this direction. Diffusion is just one along this one directions, and we know the length and the width and the thickness of the substrate, but we don't know the length, how long it is, right? So this will be considered to the as a two-dimensional case. So under this situation, how to estimate the fraction, volume fraction or area fraction? Because for the two-dimensional case, you need to know the iota will be not in the volume fraction, will be the area fraction. So based on this situation, I will draw like this. So I have a grain 1 and grain 2. In between is a thickness, grain boundary thickness delta. Then, so this area fraction, so will be, the bottom will be the d squared. D is the diameter of the grain, so d squared. And in order to know the grain boundary, the area fraction of the grain boundary, or the area of the grain boundary, we will put the d plus delta divided by 2 plus delta divided by 2 will be d plus delta squared minus d squared. So we also assume d is much larger than delta, so we will get the iota in two-dimensional case will be equals to 2 delta divided by d. Okay, so this is just for your reference. So how you need to determine the case you deal with is belongs to two-dimensional or three-dimensional. Okay. Then next, I'm going to introduce the different types of grain boundary diffusion in polycrystalline materials, and we simply classify them into 3 regions: A region, B region, and C region, based on different diffusion patterns. And before we introduce these 3 patterns, the case we deal with is we assume the grain boundary is stationary, means a stationary grain boundary. This means when diffusion happens, the grain boundary is not going to move. It's not moving. It's not moving means there's no grain growth happen inside during the diffusion process. So if you find the grain boundary moving, it probably have the grain growth stuff happen, right? So in most of cases, the temperature during diffusion will be higher, so that sometimes that will cause grain growth happens. So here we assume that the grain boundary is not moving, so means we use the lower temperature to for diffusion. And the diffusion source, actually we put them on the top of our substrate, and the bottom is our substrate is a polycrystalline materials. So you can see that there are lots of grain. Okay, so let's take a look on A region. So what we have here is the diffusion source on the top of our substrate. So within time t, means diffusion after time t, we can observe the diffusing atoms diffuse through whole material. So you can observe this gray region all the way to the bottom. This is we call the A region, and also the characteristic here is that diffusion pattern is almost cover all materials. And some people also call this A region or multiple boundary diffusion region. And let's move to the B region part. And the diffusion pattern in the B region is quite different with that in the A region, right? You can observe the diffusing atoms diffuse mainly through the grain boundary. You can see the darker region here, along here, right, along grain boundary. And if you enlarge them, you can find the diffusing atom. Some diffusing atom also jump inside the grain and diffuse limited distance inside the grain. So you can see the thicker line here means implying that the diffusing atom also diffuse into the grain, but the diffusion distance is not very long. And regarding to, and in this situation, some people also call it as an intermediate region, or because the diffusion in most of cases will be happening in the boundary region. And then we move to C region. This pattern turns out diffusing atoms directly go through the grand boundary. So, and even you enlarge this one, you find the diffusing atom all the way through the grand boundary. It turns out the atoms diffuse into the grand is very slow, so you barely can see the diffusing atom inside the grand. So in this case, some people also call it as a boundary-only region, and the diffusion pattern happen in the core-only region. The core is here. So here, my question would be, there are 3 different diffusion patterns in the polycrystalline materials. In your opinion, what parameter will lead this difference? The results would be the difference in between the diffusion inside the grain versus the diffusion into the grain boundary. Which one would be larger or faster or larger or compatible, or which one is smaller, right? So in order to, so the difference will be the difference in dxl and dB, right? So in order to demonstrate that, we use the diffusion length square root of dxlt, diffusion length inside the grain versus the grain size S, to interpret this difference. For region A, the diffusion pattern is all through whole materials. So I believe the diffusion length inside the grain means that the XLT would be smaller, equal, or larger than S. Be larger, much larger than S. So it will turn out that a diffusion pattern all through the materials. So it also implies that the square root of effective diffusivity times T is also much larger than S. This one you need to consider the dxl, all the possible diffusion paths, right? And also corresponding fractions, no matter it's volume fraction or the area fraction. Okay, so when we move to the B region, it's boundary region, or people call it the intermediate region. So consider the diffusion length. The diffusion mainly go through several grains, right? So the diffusivity inside the diffusion length inside the grain boundary will be larger than S, right? So square root of dBT larger than S, and S will be larger, who will be smaller than S? Actually, we have a tiny diffusion length inside the grain, right? Will be smaller than S. And the diffusion length inside the grain is larger than lambda. Lambda is, you can consider here, they point out, is we call the interatomic distance. I will next following slide will be talk more about what's the definition for interatomic distance. But here, we just want to point out the order for lambda usually will be range for several angstrom to several nanometer. So here, use the diffusion length inside the grain larger than lambda. Just point out the diffusion atom diffuse inside the grain. So, okay, so it for sure will be larger than lambda. And for the last one is C region, and some people call it as a boundary-only region or core-only region. This one you can see that the diffusion length inside the grain for sure is much larger than grain size. and S, who is much smaller than S, would be because diffusion inside the grain is quite small, right? You cannot see diffusing atom show inside the grain, so S much larger than lambda much larger than diffusion distance inside the grain. In this case, diffusing atom probably did jump into the grain, but because diffusion is too slow, means probably the axis is quite small. So that will lead you cannot observe any diffusing atoms show inside the grain. And also, people read you in your textbook, they highlight region B and C are isolated boundary diffusion region. Isolated boundary means what this means? This means that when you deal with some people, when you deal with, you want to explain the concentration of diffusing atom inside the grain. You want to estimate the concentration of diffusing atom inside the grain. You only need to consider one diffusion source, nearest diffusion source. You don't need to consider many diffusion sources. So isolated means you just only consider the one nearest diffusion source inside the grain boundary. For sure, because if I'm curious about the concentration of diffusion atom at here, you need to just and possible probably in the beginning you will think about, oh, probably this boundary will diffuse to control the concentration of diffusing atom probably will come from this grain boundary will contribute on the concentration of diffusing atom at inside to this page on this position or location, right? But when they highlight the isolated boundary, you just need to consider one nearest grain boundary serving as a diffusion source. So this is what we call the isolated boundary. C for sure is isolated because C for region C, when I ask you about the concentration of diffusing atom inside the grain, will be equals to 0, right? Yes. Okay, so this is a stationary boundary. But before we move to moving boundary part, I want to explain one important concept here. Why we need to learn these 3 different diffusion patterns? If actually in lecture 3, you already learn the diffusion equation, and based on 3 type diffusion couple, limited source, unlimited source, and you know the corresponding solutions for these cases, right? And you can formulate how the concentration of diffusion source change with the location and time in lecture 3, right? But the case or material system we deal with in lecture 3 is what is single crystal material, right? Because you didn't consider the materials with a crystal imperfection sign. Oh, yeah, maybe you consider that, but the questions already give you a diffusivity, effective diffusivity, so you don't need to modify the effective diffusivity. You just simply put the diffusivity inside and input the location and time, then you can get the concentration of diffusing atoms. But in most of case, in that case, actually, the material system we deal with is single crystal materials. But if the materials switch to polycrystalline materials, like this, you need to, and I also want to answer or want to ask you the concentration of diffusing atom at specific locations. How to estimate that? So to answer this question, you need to determine your cases belong to region A, B, and C. So this is why we need to classify. We want to demonstrate there are 3 different diffusion patterns in polycrystalline materials. So that can help you to answer the concentration of diffusing atom in specific location and time. Okay, so this is back to here. This is a stationary boundary, but how about if the one we deal with is the moving grand boundary? So when we have moving grand boundary, when the grain growth recrystallization happens during diffusion, that means probably this kind of case seems like, oh yes, you diffusion always you try to heat your materials up, right? So under this temperature, and the grain growth or recrystallization happens in the meantime, so that will lead to the moving grain boundary. Okay, so we want to use these very typical figures to represent the stationary boundary and the moving boundary part. So let me explain this. Because this figure is quite important, so let's take a look on the vertical axis. This is log dxlt. It's a diffusion length inside the grain. It's a square. Okay, because here we use dxlt to represent that. And the horizontal axis is a log vt. So what's the log vt? V is the boundary moving velocity we call a v. So vt means the moving distance of the grain boundary. The vertical actually is the moving distance inside the grain, but we take the square to that. So you got a log dxlt. And here we focus on the v is the moving velocity v, right? So as you expected is if vt is a moving distance of the grain boundary is smaller than lambda. Lambda is like an angstrom in angstrom or nanometer scale, right? So under this situation, this regime, is the one you just learned is we call a stationary boundary. Means the grain boundary is not moving. So it's the one you learn here is a stationary boundary. And also based on the dxlt, the value for dxlt versus the s, you got the 3 different patterns, right? So for example, this is stationary one we just talked about. So if the dxlt larger than s squared, is the one we just dxlt larger than s squared. So you take the square on this equation, you got dxlt larger than s squared. So this is region A is multiple. If dxlt in between s squared smaller than s squared larger than lambda squared is this one, then this is region B. And if dxlt is smaller than lambda squared is the region C. So here we got the region multiple, intermediate, and also the boundary. It's a core region, boundary region, and all through whole materials. It belongs to stationary one. So if the Vt is smaller than lambda means the near stationary grain boundary. This is a case we just talked about. And if the Vt the grand boundary moving distance is larger than lambda, this region, for sure, the grand growth or recrystallization happens. And under this situation, we want to explain what kind of diffusion pattern it is. So we move to the point 2 here. If the diffusion length inside the grain plus the grand boundary moving distance larger than s, so it means so here I try to draw the corresponding figures here, but we want to fully understand this description. So diffusion length in the grain plus the grand boundary moving distance is larger than s, and in these two terms, we for sure the grand boundary moving distance is much larger than diffusion length inside the grain. Under this situation, it will be like this, right? Moving distance is larger than diffusion, so but this one is larger than s, and this is grain 1, 2, and 3 larger than s, so can be somewhere here. So based on this diffusion, you can observe the diffusion pattern is all through this material, so belongs to A multiple 1. So this is VT larger S. Okay, VT larger S. And the case 3 will be the diffusion distance inside the grain plus the grand boundary moving distance smaller than S, means if it was here and this grand boundary will moving, right, and also diffusion, but everything is happen inside the grain, smaller than grain. So it will be like this. Moving plus diffusion, everything will be happen inside the grain. So you can observe a lesson. You can see some diffusion atom nearby the grain boundary, but not all through whole grain, right? So it will be similar to isolated grain boundary diffusion. So can be region B and C. The pattern can be similar to region B or C, right? So it's the one we want to talk about is this region. And it belongs to region B or region C will be depending on the dxlt, right? Will be larger and small or smaller. That means dxlt diffusion length inside the grain will be larger or smaller. So here I just want to point out is in the stationary grain boundary, region B and the border line to separate region B and C will be a horizontal line. But in here, we find it will be the boundary line will be turned out like this to separate the crystal diffusion penetration or non-crystal penetration. This border line is a straight line. So I want to demonstrate or derive why the border line is a straight line and what's the slope for this straight line. So I'm going to use a following slide to show how to get this border line. Okay. So here, diffusion penetration in crystal grain. So what we have here is we have a grain 1 on your left-handed side, grain 2 on your right-handed side. In between is a grain boundary. And the one we talk about is the case here is actually is a moving boundary. So we assume this grain boundary will be moved to right-handed side with velocity v, and v is constant. And the reason the grain boundary will be moving is what? We have a diffusing atom diffuse through the grain boundary, and some will jump to left-handed grain, some will jump to right-handed grain, and the numbers of, for sure, will be the numbers of diffusing atom jump into the left-handed grain would be much larger than that, jump into a right-handed grain, so that would push this grain boundary move toward to right-handed side with constant velocity v. So here, in order to demonstrate the flux, we make some assumptions here, and there's a very important assumption here is we assume it will be a quasi-steady state, means the concentration of diffusing atoms does not change with time, and the velocity will remain constant. Okay, so in this case, it's implying that there's no any accumulation of the diffusing atom inside the grain boundary. So the flux into the forward grain can be formulated as the flux equals to negative diffusivity dxl concentration gradient. And due to the reference coordinates moving to your right-handed side, before diffusion happened, it was here, but after time t, diffusion happens, and the coordinate reference move to here. So the flux, because the reference moving, so the flux you need to minus this extra flux due to the coordinate reference moving. So means this flux is not really due to the flux into this forward grain. It's due to the coordinate reference moving. So you need to minus the VC. And because we have this kind of assumption, so if it is a quasi-steady state, it means the concentration of diffusing atom does not change with time. So we take the divergence of the flux will be equals to 0. This time divergence will be equals to 0, so this one will be the constant. So you can get the solution for concentration of diffusing atom expressed like this: C0 times exponential term. In order to simplify this, we divided by v together. So we got this minus x and dxl divided by v. So here we know the concentration of diffusing atom dramatically decrease based on this exponential term. Okay? And this is a grain boundary, right? Don't forget this is grain boundary. So we got the diffusing atom diffuse through grain boundary, then it will diffuse into the grain by this exponential term. And the exponential term, if we assume this dxl versus v equals to lambda, and what this means, when x equals to lambda, means this x equals to lambda, the concentration, this location, the concentration at this location will be equals to C0 times exponential minus 1 is the relaxation time you learned before. Okay? Okay, so let's move the first we want to demonstrate the borderline in between this one and this one, this borderline, right? So let's move forward. So dxl equals to dxl divided by v equals to lambda. So we times t together. So times t and take a log. So you got log dxlt log vt plus log lambda. So if you use this as a y-axis, this is the x-axis, is the one we just talked about. Y, x, so the slope will be equals to 1. So we already show you the borderline straight will be the straight line with slope 1. And at this moment, you probably will have a question. The lambda, professor, is a lambda interatomic distance you mentioned, because actually we just use in in here, we give a promise to you that we want to explain what's the interatomic distance, right? Yes. The lambda is the same. Lambda is the interatomic distance. So lambda actually, the specific value for the lambda is dxlt divided by the moving velocity of the grand boundary. Will be different in different matrix systems. Okay, but some people probably were curious about why this is equals to lambda. So I have my handwriting here. In the beginning, I can, instead of u equals to lambda, I can just assume equals to beta, an unknown parameter, and I just times the t together and take a log and put this back to the figure on the page 10. And I use the data point, I use lambda square and lambda square and lambda here. Then for I prove that beta equals to lambda. So here I just want to show you this lambda is really the lambda we show you in previous slide. And by the way, I want to explain one more thing. Could you expect it? The value for the lambda on the boundary, on the grand boundary, the diffusing concentration of diffusing atom will be equals to C0, right? So lambda, when lambda, what this means? Lambda is the talking about the concentration of diffusing atom drop down to exponential -1 to -1. So if exponential -1 is this value, so my question would be, if we have a small lambda in this is small lambda, right? Because at this lambda, this is small lambda. The other one is like this. This lambda, when the let me back to also the grand boundary here C0. I need to redraw again. Okay, if I assume this concentration is C0 times exponential -1, drop to this one. Okay, so lambda, the value for lambda is quite important, so I want to show you. If this one, I will say this lambda is smaller, and the other case will be I use the other color for this one. If the concentration inside the grand, the profile, let's say you have a lambda, larger lambda, right? Lambda larger, this is lambda smaller, as smaller. So lambda larger one is similar to region BOC, or smaller lambda is similar to region BOC. I will say this belongs to B, because you can see diffusing atom diffuse into the grand, and this one small lambda is more similar to region C. The diffusing atom, most diffusing atom is still nearby the grand boundary, just tiny diffuse into the grand. Okay, so based on this concept, we move forward. So when the lambda, if you move the V here, lambda is larger, then that will be belongs to lambda is larger, then it's a crystal diffusion penetration. It's similar to region B. And if lambda is smaller, it's non-crystal penetration. Okay? So let's move to next slide. Here you already know these figures. You know more about no matter is stationary or non-stationary group boundary, you know the diffusion patterns in these polycrystalline materials. So now we want to move to the one I just mentioned. I just asked you, if we have a polycrystalline material now, and can you answer me the concentration of diffusing atom at specific location and time? So first of all, you need to use this criteria to determine what type of diffusion pattern we're dealing with. If it belongs to region A, through whole diffusion or through whole materials, then you can use the solutions you learn in lecture 3 to answer the concentration of diffusing atoms at specific location and time. But if it belongs to region B and C, then we need to talk more and show you how to deal with this. But probably because time is limited, so today we just end it here.